This video is going to start with a cat, a Schrodinger's cat, the cat that's both dead and alive inside this basket. And that's because today we're going to discuss quantum mechanics. And I guess also because this video is just kind of super cute. But anyway, a much more appropriate first image to show you would be this. The image that was recently shown to us by the scientists whose paper we're discussing today. This image shows us particle-wave duality. The cat that's both dead and alive, but in actual physical image. And this is technically the first such image ever produced. But in order to understand what we're looking at, we're going to discuss how this was achieved, and of course exactly what you're looking at. And so, hello wonderful person, this is Anton, and this is a Schrodinger's cat. And today we're going to discuss a study that you can find in the description below that was able to produce yet another physical proof of the particle-wave duality by taking a picture of single atom wave packets that are both particles and waves. The theoretical principle that was originally proposed by the French physicist Louis de Broglie in 1924. He was essentially the first to propose that electrons can technically act like both particles and waves and form the theory known as electronic waves. And just a little bit after this, Edwin Schrödinger was able to form an equation explaining everything. Today we refer to this as the Schrödinger's wave equation. The equation that predicts how particles turn into waves and how they should behave as a result. Here's actually a really cool visualization showing us this equation in a nutshell. This is essentially a visualization of the so-called wave packet. Here's a much more simpler one in 2 dimensions, and here's another one where all of this was replaced by different colors. And naturally this equation is very well known and has been proven to be correct many times. As a matter of fact, it only took a few years to prove that electrons are indeed both particles and waves. One of the first such experiments was from 1923 to 1927 by Clinton Davison and Lester Germer. And this was an experiment using electrons scattered by a single crystal of nickel that would then produce a kind of a diffraction pattern, kind of producing something similar to the famous double slit experiment, but just much simpler, with more and more experiments confirming the results. Basically confirming that pretty much all atoms exist as packets of wave-like probability in space, but that tend to actually collapse into individual particles once they're observed. Why this happens and exactly what happens is not really going to be the purpose of this video, as there are actually so many interpretations and explanations, and we'll talk about this in some of the other videos, or you can learn more in some of the videos in the description. But we just know that it does happen, and pretty much all particles exist as waves defined by Schrödinger equation. And technically it's not just particles, it's really all matter. We've actually discussed some of the newer experiments that were able to turn even larger objects, or so-called macro objects, into these wave packets as well. But that requires some extreme conditions and is not something we're going to be observing around us in daily lives. But if you're curious, check out that video, that should be somewhere right there. But let's discuss this experiment and what exactly this shows us as well. First of all, what you're looking at is lithium, specifically an isotope known as lithium-6. And here, each of the lithium atoms is essentially cooled down to near absolute zero by basically using powerful magnets combined with photons of lasers that stop these atoms from vibrating and thus make them reach almost absolute zero temperatures. And it's at these temperatures that atoms start to act as quantum objects. Although here the atoms are also confined by using a special optical lattice in order to prevent them from moving. And so basically lasers do most of the work in both holding them and in cooling them down. And this is actually a relatively well-known technique that uses a device known as quantum gas microscope. This was officially revealed back in 2009, and you can read about this device in one of the articles in the description. But basically its purpose was to try to visualize individual particles in a lot of supercooled gases in order to study quantum effects. And so by using a slightly modified version of this, here the researchers used lithium and were able to visualize individual atoms' changes in time. And so essentially what they did was take a snapshot, which would actually reveal tiny particles across the image, but they would do this when all of these atoms were locked in place. They would then release them for just a little bit and capture them again, taking the next snapshot. And so every time they took a snapshot, we would see a particle. This is of course the famous wave collapse. But in between shots, each of these atoms would return to its wave packet state and could thus then appear in a slightly different location as predicted by Schrödinger's equation. And so basically, even though these were locked particles and should have been always in the same place if they were particles, because this is a quantum system, each of these particles would appear in a slightly different place after every single shot. And so they did this many times, taking continuous snapshots which made these dots appear larger and fuzzier over time. But most importantly, they would actually appear as predicted by the wave equation, literally showing us what a wave packet looks like in real life. And so basically here, we're just seeing the light emitted by each of these atoms as they go in between their wave and particle states. And they only become particles when we're taking that picture. In this case, the Schrödinger equation does predict that a wave packet is technically free to move around to some extent, even if it's held by something in place. And so it should appear fuzzier and much larger than just a single particle. But in a nutshell, we're just looking at a combination of many different images all combined into one. So I guess you would call this a time-lapse, basically presenting us with yet another, and actually a much more impressive visualization of the famous wave-particle duality. Literally, the main principle of quantum mechanics. But in terms of more technical achievements, or what this means for science, well, this is just a new technique that allows high-resolution imaging using quantum gas microscopy in order to take snapshots of individual single-atom wave functions at different points of time. And so here the scientists were able to achieve extreme control of everything, fixing atoms in place, and even imaging them without destroying their quantum state, which technically should open a lot of doors for quantum physics research and a lot of quantum simulations. And so obviously for fields like quantum computing, but I guess for physics, this is even important in order to help us understand what might happen inside extreme objects such as neutron stars, where we actually believe a lot of quantum effects take place as well, or what might have existed during the first milliseconds after the Big Bang. And so here, by basically replacing lithium with maybe something else, and by changing the experiment just a little bit, it becomes possible to visualize quantum effects in some of the most extreme conditions we would never see otherwise. Understanding strange states of matter, with one of the first predictions being that we might be able to now form completely new states of matter that we never knew existed. States of matter that we cannot even predict yet, but that could be formed in these conditions. So basically this opens the door to a lot of new experimentation. But for us laymen, it's just a really cool picture. Kind of like that first picture of the black hole that basically shocked everyone. And now we have the first picture of some of the smallest things acting like waves and particles. So yeah, maybe I should put it on a t-shirt. Maybe some other day. Anyway, on that note, once there are some additional discoveries, or once there are some more cool images and cool pictures in the realm of quantum physics, we'll come back and talk more about this in some of the future videos. Until then, check out some of the other similar discoveries in previous videos in the description. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.